Michel Gomez, the head of the mathematics department. And I'd like to welcome all of you to the 2024 Simon's Lectures in Applied Math. This is actually the second series of Simon's Lectures in the department. This year we had Elan Lindenstrauss a few weeks ago give us lectures on homogeneous dynamics. So the Simon's Lectures is the most prestigious set of lectures in the department. They were established about 25 years ago by a generous gift from Jim and Marilyn Simons, whose philanthropy in math, physics, and computer science is really unparalleled. And so today I'm happy to have Lenka Zdeborova give these lectures at the intersection of all these fields. So Lenka is a professor in physics and computer science at EPFL in Lausanne, Switzerland. She received her PhD in physics from the Université Paris-Sud and also from Charles University in Prague in 2008. For 10 years she was at the CNRS, at the Institute for Theoretical Physics, where she was director de recherche. I'm sure that my French is perfect. Wow. I'm even impressing the real French guy. Since so Lenka Zdeborova is interested in how principles and techniques from statistical physics leads to results and approaches for challenging computation problems. And instead of lectures is on computation through the lens of spin glasses. And today, our first lecture is on phase transitions in computational problems. And phase transitions is a really important phenomenon in statistical physics. So her honors include the CNRS Bronze Medal, the Philippe Meyer Prize in Theoretical Physics, the Joliot-Curie Prize in 2018, and also delivering the annual AMS Gibbs Lecture in 2020. And looking through people who got the Gibbs Lecture, it seems that there is a huge intersection between the Gibbs Lectures and the Simon's Lectures. So we have had many of them over the years. So I don't want to take more of your own time. You came to listen to her, so please join me in giving a warm welcome.
Thank you so much. I feel honored and super happy. It is on. I'm on it, don't worry. Super happy to see old friends and also to meet new friends and to tell you about, kind of line of work. I will start today quite high level, going back to maybe not the beginnings, but some time ago, and then we will progressively go to something more recent. So I was thinking of a picture like that when I sent this title, Computation Through the Lens of Spin Glasses. So you kind of see through the lenses, more focused. Maybe you don't see the whole picture, not everything, but what you see it in detail. So that's kind of how I want to you maybe to think about the title. And one thing that should be said is that that's a line of work that I'm looking through the lens of spin glasses for about 20 years, not alone, with this guy, Florent Chakala. We wrote over 110 papers together, so that's a lot. I mean, raise your hand if you have a co-author with whom you have more than Okay, so yeah. Anyway, so in these 3 lectures, I try to give you the concepts, the ideas, the exciting things. If you want about details, how the calculations actually go, we have this doctoral lecture that is online with the lecture notes and all the recordings. Thank you, COVID. And next spring, that will be probably given also at UC Berkeley. So if some of you kind of switch, that's a usual switch, then you can attend it. one more kind of general slide. How I think of my research is something like this, okay? So I see you're laughing, so you have already seen this quantum mechanical notation. So you might also see the point I want to make here is that when a classical observer observes this composition of pure states, they usually collapse it to one of the pure states, right? So you need to be a quantum observer, or you need to kind of be versed in the quantum world to see that it's a composition of things, superposition, and that it's not as simple as collapsing to one of the things. At least that's how I would like to think about it. So as said, I will start with phase transitions in computational problems today, and tomorrow and the day after, something more about neural networks, maybe going to things like attention and algorithms descending complicated landscapes. But let me start with the phase transitions. So since these are lectures in math, and I can kind of assume that computer science and machine learning is today everywhere, so you're maybe versed in that. So maybe the background that we miss the most in the audience is the physics. So I will start with some high school physics to kind of get on the line of what these phase transitions actually are. So this is the phase diagram of water. As a function of the temperature and the pressure, we have the three phases: water, vapor, water, liquid, ice. There is this three critical point over there, above which there is no difference between water and vapor anymore. So that's how we represent things in physics, and you may have seen that somewhere at high school. It's probably hard to kind of understand the scale of the temperatures and the scale of what the pressure is. For that, I love to see this picture plotted with the atmosphere on Venus over there and with the atmosphere of Mars over there. So quite curiously, Venus is close to the three critical point and Mars is close to this three critical point. So that's kind of to get what the range of temperatures and pressures actually is to kind of explore this phase diagram. So another way to represent things that will actually, you will see, we will be plotting very similarly looking pictures later on, is something when you actually take water and the liquid gas transitions. So you take water and its density as a function of the temperature. So the different curves are different atmospheric pressures. So 1 atmosphere is this number, right? So you know that at 100 degrees Celsius, water evaporates, meaning that the density discontinuously jumps not to zero. This is just much smaller density of the gas than of the water, right? And when you do the same thing at higher pressure, this happens a bit later at higher temperature. And then at this three critical point, it becomes continuous. And later on, it does not happen. So this kind of dependence of one quantity on another quantity, right? This is what we kind of teach in undergraduate physics. Now, mathematically, where does this come from? So this was a big question in physics about 100 years ago. And quite strikingly, the existence of phase transitions of these sharp changes in behavior comes purely from the fact that there is a lot of molecules, something like 10 to the 23, interacting together. Nothing microscopically changes, just the fact that things are random and many makes certain random probability measures concentrate. And then the physical quantities, when we draw a picture like that, it just means that some quantity is with high probability the same in every possible instance, not every, but the probability that is different is so small that it never happens in physics. So we are plotting the density as a quantity that concentrates in this limit of large size. That will be the high dimensional limit in, say, statistics or computational problems. So that's what's happening here. There is one more curious thing related to the phase transition in water, that is metastability. And you can illustrate it here, where you took water, you put it, very clean water, you put it to the freezer, so say you cooled it to say minus 10 degrees Celsius, it should freeze. But since it's very clean, it did not freeze, it supercooled, it stayed liquid. But now what you do when you actually hit the bottle then there is some impurity that will come up of the plastic or it will hit the cover, and that will induce nucleation, the ice that is growing in the water. And at the same time, it will release heat, because actually the ice was the equilibrium state here and not the water. So this will at the same time warm up. And another kind of phenomena that you can observe, where, for which this same phenomena is responsible, is this freezing rain. In the clouds, the water can get super cooled. When it falls on an impurity, immediately it freezes. It creates a crazy picture like that. There are some materials that are in this supercooled state, in this metastable state, and if you don't know, you may be surprised. The diamond is one of them. That actually, so this is again a phase diagram of diamond. Now the range of temperatures is huge. The range of pressures is also huge. And this line over here, so this is very big pressure. Above that pressure, diamond is actually the equilibrium of state. Below the equilibrium is the graphite, the thing that we are writing with, not the diamond. Yet, at normal pressure here would be actually somewhere, and it's not even plotted, and temperature is somewhere really small. So in this region here, the diamond that we observe is actually metastable. If it turned into graphite, it would be happier, it would release heat, but it doesn't happen, right? We are not worried about that. So this metastability in physics is curious, interesting. So that's it for the physics, okay? Now let's go to the computation. And now I will introduce you an example with, it will be a very simple example. You may think, okay, why we are dealing with such a silly problem? But we actually will cover many things by dealing with this problem. We will illustrate how we actually study the phase transitions in physics on simplified solvable models. We will present the first, because you will see I will present it as a computational problem. At first it will not look as physics to you, so we will present this relation between the physics and computational problems. And on the way, we will explain what's a spin glass, because you tell me, okay, it's very nice that you're looking at computation through the lens of spin glasses, but I don't know what's a spin glass. And don't worry, this example will teach you what's a spin glass as well. So I like to put it as a spin glass card game. So we have an audience of here 15 people. Imagine I have a deck of cards. Roughly half of the deck is +1, roughly half of it is -1. I shuffle it, and I randomly deal the cards, one card to each person. And so I deal the cards. And now the game will be, I have to guess. I have to split the room in 2 groups, so that in one of the groups, most of the people have the same card. That will be the game, right? But okay, I'm not a magician. I cannot do it without observing anything. So I will observe something, and I will observe the following thing. I will pick some pairs among you, and for each of the pairs I pick, I will ask the following thing. I will give you, for instance, a 4-sided dice, and I will ask you, draw the dice. Don't show me what you draw, but if you draw 4, I ask you question, do you have the same card? If you draw 4, then you lie. Okay, so if you don't have the same card, but you answer yes, so you lie. And if you draw 1, 2, or 3, then you tell the truth. So if you did not have the same cards, you say no, we don't have the same cards. Okay, so that's what I observe. And I do this for many pairs. And now how many pairs? This will be my kind of signal-to-noise ratio. Right? The more pairs I query, the more information I have, the easier it will be. So I do this for many pairs, and here is just represented. Yellow are the guys that drew 4, so those are the ones that lied. So you can kind of check that the product of their cards is disagreeing with what they told me. And the ones that are not yellow, those drew something else, so they did not lie. And then, but I don't observe, okay, I can forget about the people. And I also did not see who drew what, so the colors disappear. And also I did not observe who had which card. So the only thing I observe are these answers. I pick the graph, the edges at random, it's a random graph. On n nodes, I observe for everybody on average C questions. So then the probability with which I draw the edge is C over n. create an Erdős-Rényi random graph, collect the answers on each of the edges, and that's now my information I can work with to actually split the room into two groups. So this is some kind of a clustering problem, right? Clustering of graph problems. So it's a nice problem in computer science that we can look at. So let's look at it. How do we solve it? So I define things very explicitly. I can just formalize things. Okay, the cards are plus minus ones. I will call them some A stars. The answers, Jij's, are plus minus ones on the edge ij. And I will call rho the bias of the dice. So the 1/4. How often do you lie? And then from the definition of the problem, the probability that I observe a given answer on a given edge, given the colors, is simply given like that. That's just rewriting the definition of the game. And because these things are binary, you can actually examine this expression and realize that it's equal to this expression if by beta I call this simple transformation of the row. Okay, so this you will maybe need 2 lines to actually persuade yourself of that, but it's completely elementary. So you realize that, and with that you can rewrite the posterior probability distribution, so the probability of what were the original cards given what I observed, the J, using simply the base formula and the form that I just wrote you in this form up here. And that's what in physics we call the Boltzmann measure of a spin glass. Okay, so if you did not know what's a spin glass, this is a spin glass, right? Now you don't need to think of anything else. So we are interested to understand this probability measure. And we also know that the optimal split of the room into 2 groups where most people have the same card boils down to computing the posterior marginals. That means to take this probability measure on n variables and sum over everybody except one node, and then the marginal probability is my estimator for how to split the room. So this we can prove in few lines. And the Jij, that's the only thing at which at the end depends. I remind it's given by the definition of the game. So this is elementary, we know how to do that, but in order to compute the marginals computationally, we need to sum over 2 to the n minus 1, but who cares about minus 1 terms? So this is not efficient. This is in principle a way to solve it, but not an efficient way to solve it. So now we can ask a question, so A, what is the optimal performance if we actually ignored the computation complexity? And B, can this optimal performance be achieved with a polynomial algorithm? And now this comes line of work in physics in the past century, starting from Hans Bethe, who got a Nobel Prize in physics for realizing the reaction by which sun shines. But here's this one paper where he looks at a very related problem as this one and realizes, but actually looks at the graph that is a tree, not a random graph, a tree, and writes relations between the marginals / magnetizations in physics on a model of a magnet. And then David Thales, who's another physics Nobel laureate for yet something else, realizes that the same trick can actually be done with disorder, meaning when the interactions, the answers are actually not all +1, but maybe ±1, and that it still works, but it's still on the trees. And this is 86, Bethe is 35, so it took 50 years kind of to get to the disordered systems. Soon together, Mézard and Parisi, they realized that you actually don't have to be on trees. That this set of iterative equations is actually the right thing also when you're on a random graph. That is not a tree globally, but locally it is a tree if the degree is fixed. And they realized that and applied the same equations. And then yet some 10 years or so later, Kabashima and Sard realized, oh look, this is not only an analysis technique, because early in physics they were using to analyze the phase transitions in these systems, but they were not thinking about algorithms. And Sard and Kabashima realized this is related to an algorithm that is called belief propagation that came about in information theory, thinking about error correcting codes. And they realized that this algorithm is essentially the same, or not essentially, it is the same equations. It is the same iterations of what you need to do. And all this together gives us a prediction that an optimal way to solve our spin glass game is the following. You write belief propagation or beta approximation, which has this form. So the quantities, the beta is related to the raw, right? The j's are the answers. The only thing that I didn't define is are these u's. Those are messages. So for each time iteration time t, k and I are nodes. So we think of these as messages being sent between nodes of the graph. So each edge has one message in one direction and another message in another direction. And then this line of work predicts that if you initialize this at random and iterate till convergence, so first in this particular case it will converge, and then when you use the fixed point to compute the beta marginals / magnetizations in the physics notation this way, then this leads you to an optimal estimator, in the sense that as the room is large, n goes to infinity, this is matching, this is the performance of this algorithm, like how many people in the same group will have the same cards. That's a number that concentrates on some specific value that we can actually compute. That's the prediction, with no proofs from this line of works. Okay, so now this is a lecture in mathematics. So here is just a selection, small selection of works where this kind of prediction is being established, or partially being established rigorously. So the first point is, in the form that I stated it, is that this belief propagation algorithm, randomly initialized, actually converges to the optimal estimator as n goes to infinity in the leading order, is still open. This we still don't know how to kind of finish that completely. So as maybe somebody in the room has some ongoing work that I'm not aware of. So this is still open, but we have results that lead there. So first of all, if the graph was not sparse, but dense, the degree went to infinity as n goes to infinity, so maybe it would be proportional to n, or maybe some logarithm to some power, then in that limit we actually know how to prove that versions of this belief propagation, which in that case is called approximate message passing, that it's actually an optimal algorithm to get the optimal estimator, and this would be some of the works. We also know how to prove optimality of the belief propagation if actually a fraction of the cards were revealed. If I asked 1% of you to show your card, then this would be enough for the proof to go through. And that's actually works. Many of these names are actually people around. Oh, now the audience is big, I don't see if everybody is here. If it was for the ferromagnet where all the answers were kind of one, or for that version we also know how to prove that. If we were actually not going after the algorithm but just about the value of the optimal accuracy, this also we know how to show that that's the right characterization. And if we were going, okay, we'll show you the threshold and the contiguity to random graphs, then we also know how to do that. But fully kind of this is ongoing work and kind of inspired a lot of work in math. But let me show you the result and the properties of what's happening here, right? Without kind of now skipping the details of how one gets there. So what is plotted here is the fraction of correctly grouped nodes as a function of how many pairs I queried per node. And you see that there is as I said, the more pairs I queried, the more information I have, so the better I should be doing the job. But what kind of is not intuitive, at least it doesn't naturally kind of come up as your first guess, is that this curve actually gives you half, which means you just if I split the room at random, I will have half people that have the same card, so that's a trivial result. So I'm not doing better than random until I queried twice the number of nodes. And once I queried twice the number of nodes, then I start to be doing better than random. And this is solving numerically the equations on some given size, but in the limit of large n, this would go to a curve that is well defined, and there is one kind of master curve, and this quantity concentrates on that curve. Where this threshold is, how many pairs I need to query to actually start to be doing better than random, can be very simply expressed using the bias of the dice, which for us was 3/4. You were telling me the truth. So the row, if you choose something else, this gives you the threshold. And this is a phase transition. On the way, what I did is, if I was actually teaching you how to describe that a magnet that is on your fridge, if you heat it up to something like 700 Celsius, 1000 Kelvin, then it will fall off the fridge because it will stop to be magnetic. Okay, so there is a phase transition like that, where magnetization appears at low temperatures but not at high temperatures. So this would be high temperature, this would be low temperature. And when I cited these works of Bethe in 35, so almost 100 years ago, that was his goal, to actually understand why that happens and where that comes from mathematically, that at high temperature magnet falls off the fridge. And the model he constructed, since he was using the Bethe lattice, so this tree that is the same as the random graph locally, was really this model. So our early understanding of where phase transitions in physics, how they appear and how mathematically we can describe them, is based exactly on this type of model, as our kind of spin glass game that I am presenting here to you as some kind of toy example to understand things, but also as a toy model for data clustering. Right? Many of you may be working with some people in applications. You know that clustering of data is a very important problem. So this is, of course, not solving all the possible problems that you may come up with if you actually practically want to solve data clustering, absolutely in the same sense as realizing that the model of the ferromagnet behaves this way does not explain at what exact temperature it happens in the real materials, how it will depend exactly on which material it is, how it will depend on the molecules that constitute the material. All these details kind of are not there. And in the completely same sense, this is modeling data clustering, but is putting aside a lot of the details, but keeping enough in to make it non-trivial and interesting, to make the phenomena of the phase transition pop up, and to make a setting where we can understand things in detail, even though in practice, the details complicate things, and we may not be able to get such a sharp prediction and mathematically provable theory of what's going on. So that's for this model. Now, in magnets, this is like the density of the water changing with temperature, and you see that here it is continuous, right? Either it's continuous. Whereas in the picture that I showed you for the water, at the evaporation point, the density changes discontinuously. So in physics, we call the continuous ones second-order phase transitions, and the discontinuous ones first-order phase transitions. So in water, it's a first-order phase transition. Now, can we get a first-order phase transition in a computational problem, and what are its consequences, right? Here, so far, we had a second-order phase transition. We had an algorithm that was achieving optimal performance. Okay, yeah, kind of, okay, nice. But now what happens when we have first-order phase transitions, such as those in water? So first of all, is there some way to change our card game to make it have a first-order phase transition? Let's make a variant. Okay, now I have 3 values of cards, blue, red, and green. Again, the same fraction of each. I deal it to the audience. Again, I need to observe something so that I'm able to recover the cards back from the observations. The observations now are a bit different. I deal the cards, and then what you are giving me is, I choose at random pairs, or you choose. I don't see the cards, so the colors, so I cannot do this. But you choose at random among the pairs that have different colors. So if you two have different colors, You may be one of those pairs, so you raise both hands. I note you and you have different colors. The same for you. If you have actually the same color, then you don't raise your hands. I don't know. I mean, to me, those that didn't tell me anything or those that have the same colors, it's all the same. So I only observe pairs who had different colors. This is a kind of planted coloring problem, right? I will create a graph, and then the assignment of the colors to the nodes of the graph will be a valid coloring of the graph. But I started with a valid coloring of the graph. So I did not create a random graph. I create a random graph conditioned to the fact that a given configuration is its valid coloring. So I call it planted coloring version of the game. So I create the graph, I repeat that m times. M will be the number of edges. That creates a graph. You know that naively doesn't look very different from R-Renyi, but it's not R-Renyi, right? At high number of edges, R-Renyi graph is not colorable with 3 colors. This one always is, by definition. And then the question I'm asking is who had which cards? Because of the permutational symmetry, to put it properly, find groups of nodes that have the same card. And the answer is similar, unsurprisingly. That again, we write things as a Boltzmann distribution. This time in physics, we would call this a Potts model. It's a distribution over n variables that take a value in the alphabet of the number of colors that we have. The belief propagation algorithm looks like that, where this kind of neighborhood relation is just a neighborhood on the graph. And I need one more equation. That is called the Bethe free entropy. That once I iterated this, t here are iteration indices in the algorithm. The fixed point, I plug it into this expression. And then the theorem from this paper informally said is that in the large size limit, the optimal accuracy, so far irrespectively of whether I can do it efficiently or not, is given by a fixed point of this belief propagation that has the largest free entropy. That's the prediction. And now, okay, let's examine how the fixed points look like. So now we will realize that actually before we had a unique fixed point with high probability given a random initialization, we always reach the same fixed point of this iterative process. Now it is not quite true. So if we initialize randomly, we reach a fixed point which corresponds to the blue points. Now this is some kind of accuracy that is 0 if I'm just randomly guessing, and 1 if I get exactly everybody right. And in blue, I actually initialize in the ground truth. So that's of course not a valid algorithm, that's cheating, but for the purpose of the analysis, I can imagine it, that I initialize those messages in the algorithm in such a way that they all start with the right color that you actually had, which of course is not an algorithm, but for the purpose of the analysis, I can think about it. And the blue and green overlap here and over there. When you don't see two curves, it's because they overlap. But in this intermediate regimes, they are different. And when they're different, then the red curve here, that's actually telling me which of the free entropies is better. So the so overall, now here it's maybe a bit small, but the point where the two fixed points become the same and the point where the free entropy crosses 0 are actually not the same. These are two distinct points. Number of questions over size, either I will call it CD for the threshold where the two fixed points start to be the same, or I will call it CIT for where the red curve crosses, or I will call it C-alg, the other one, where the other point where the two fixed points start becoming the same. And if I now translate what the theorem said, and the fact that running from a random initialization is a valid algorithm. So if that algorithm gets the optimal performance, then that's it. I have the optimal performance. And if it doesn't get it, well, then that's a phase where it's possible to get it from the theorem, but this algorithm doesn't get it. So that's what I call the hard phase. So I split now. If I have too few questions, it's just impossible to get any correlation, just as it was before. Again, this is not self-obvious that it will be completely impossible, but that's the case. Then there is this intermediate regime where it's possible if I had exponentially costly procedure, but the belief propagation algorithm doesn't do it. And then there is a regime where this algorithm gets me the optimal performance as it did before. Okay, so once again, summarized. The green region, easy, belief propagation is optimal. The purple region, impossible, nothing, no procedure can give me any correlation with the ground truth. And then there is the hard phase where this algorithm doesn't manage. But more than that, we actually dare to conjecture something like that no polynomial algorithm will manage. So that's daring to say something like that based on one algorithm. True. But that conjecture was made in a paper now 13 years ago, 14 almost, and it still stands. So it may be true. So the nature in which exactly it is true from computational complexity point of view, it's a topic of many ongoing and past works. It's a very fascinating topic. In which exact sense is this phase actually hard? And in why really no other algorithm can get us a correlation in this problem. But this conjecture seems to stand. So if I now kind of make the analogy back with physics, if we were, the impossible phase would be like the liquid, and the easy phase would be like the ice, if our goal was to crystallize. And then the computationally hard phase would be the supercooled liquid that in the freezer did not crystallize. Only once we hit it and introduced impurity, it actually crystallized. But that's something that does not happen. I will explain in a moment kind of what is missing here. So the fact that the water crystallized, that happens for a particular reason, that in the computational problems on random graph doesn't happen. I can maybe say it now. Because the water lives, oh, it's actually written here. Yes, right. So what's the difference between the water versus the coloring game? Why the water crystallizes if we hit it? Whereas in the planted coloring, this is really computationally hard and we don't know what to do about it, or at least conjectured hard and we don't know what to do about it, is the simple fact that water lives in finite dimensional space, whereas a random graph is effectively infinite dimensional. So in finite dimensional space, what happens is when you create a large droplet, eventually the volume will become bigger than the surface. And this is something that is responsible for the fact that the difference of the free energies between the two phases actually eventually wins. And around some impurity that is created in the material, the stable phase will eventually grow, and it will not take exponential time to do so. But on a geometry where surface is always as big as the volume, which is always the case on a tree, like the number of nodes inside is roughly proportional to the number of nodes on the boundary. That's true however big neighborhood I take, unless I start closing the loops. So this kind of nucleation is not induced in the random graph geometry, and hence the metastability stays there for exponential time. At least that's the kind of physics explanation of what's happening. It of course is not an explanation for why some other algorithmic idea that can be completely crazy and transforming the problem to a completely different space of variables or some kind of relaxation where all these notions lose sense, why this cannot help and cannot bring a polynomial algorithm. But that seems to be the case. But this analogy alone doesn't explain it. And going back from to the diamond is a bit the other way around, right? With diamond, we are happy that it stays diamond, that it doesn't turn into the stable graphite. That would be disappointing. Whereas here, we are unhappy about staying in the bad performance fixed point and not getting the good performance. So in this point of view, it's the other way around. So now, one point of comparison, our card game, I said it's a planted coloring. So it's a type of a clustering problem where the relations I observe are disassortative and kind of only people that are different actually have edges between them. But coloring problem is interesting per se, and coloring of random graphs is very interesting, was studied in mathematics. So it's interesting to make the analogy between the three phase transitions that I described. Now I call it alpha, not SC, because it's some kind of generic signal to noise ratio. So the bigger signal I have, the more I'm on the right. So what these blobs mean, so each of the squares would be different value of the signal to noise ratio. And the kind of blue pixels, or black in the first case, represent so the square represents all the combinations of configurations that are possible. So the say number of colors to the n possibilities. And if they are colored, it means that they are valid colorings. Either black, red, or blue, those are all valid colorings. And if they are white, it means they are not valid colorings. So there are all those configurations. Some are valid colorings, some are not. And then it's interesting what actually happens with these, with the structure of these valid colorings as we increase the signal to noise ratio. And the three thresholds that I described so far for our planted coloring problem, they translate to what's happening in the random coloring problem. This one where the two fixed points are not the same anymore corresponds to the clustering in random coloring, where the space of solutions is not one blob anymore, but splits into exponentially many blobs. And the information theoretic threshold, where with an exponential procedure I start to be able to get a correlation, corresponds to what's called condensation threshold in the random graph coloring, where the measure is not supported anymore on exponentially many blobs, but only at few blobs. Then there is the colorability threshold at some point, where I lose all the valid colorings. That doesn't have really, I mean, it has analog in the planted problems in the sense that all the other clusters but the planted one, the red corresponds to the planted configuration, the ground truth one. The others disappear. But that doesn't affect my ability to recover the planted one. And then at the algorithmic threshold at which the belief propagations start to work, that corresponds to the Kesten-Stignum threshold in the random graph coloring. So, okay, this is maybe for the part of the audience who are kind of aware of the phenomenology on random graph coloring. A note that I want to make here is that now today I'm talking about the inference problem, where these thresholds are well defined. This hard phase conjecture seems to stand. We still don't have algorithms that work there. I believe that they don't exist. The problem in random coloring is more optimization or exploring the landscape. I will talk about those more on Thursday. But there is another natural computational question here, and that's the one of sampling. If we actually wanted to sample uniformly at random all those configurations, we wanted to sample from the posterior. That is useful in machine learning, in statistical inference, for instance, to compute uncertainties, to compute variances of things. It's useful to sample and things like that. So sampling is interesting. This threshold here, that the alpha D, that I defined, but it didn't have any particular meaning for possibility or hardness of solving the inference problem, it actually has a meaning for the sampling. The conjecture is that before this threshold, it is easy to sample in some weak sense, in the sense that properties that concentrate will converge to their correct values if we sample with Monte Carlo Markov chains on that side. And sharply at alpha D, this will stop to be true in polynomial time. We would have to run the samples for exponential time to actually sample in a phase like that. So this threshold has a specific meaning for sampling. Again, this is conjecture. Proving something like that, as far as I know, is still open, because it's very hard to analyze explicitly what Monte Carlo Markov chains in this regime actually go, because we would have to restrict them to only short time in a very complex setting, or the Lanzervan algorithm the same. What's interesting is we can also ask sampling for the planted coloring on the right-hand side. Can we actually sample that little blob there? I will talk more about it tomorrow, that if we sample with Monte Carlo or Langevin, we will actually not manage starting from alpha alg. There is an additional gap for sampling that is interesting, has interesting consequences in machine learning, at least I think so. I will try to describe tomorrow. But if we use fancier samplers that, today I would say they are based on diffusion models or flow-based algorithms, those that, generate all those amazing pictures in things like Midjourney or these generative models, these AI models. So the procedure that is running behind that, we can also use it as a sampler from a probability distribution that we know, that we don't even, if we know the probability distribution, we don't need to learn it from data, but will those procedures actually be able to sample? So they will be able to sample starting from alpha alg. It's kind of interesting, but they will not be sampling up to alpha d. There will be a gap. So that's some, like discrepancies between ability to sample of the classical kind of Monte Carlo and the more modern kind of diffusion-based samplers that in these papers are kind of clarified and described, if you're interested in sampling. This is another kind of zoology graph showing that the phase transitions and the way these curves describe that I show this one, the second order phase transition from, here is the error as a function of signal to noise ratio. Rho means that we are just randomly guessing. So either we are randomly guessing or doing better. And it can also have this shape with the hard phase. So that's just one possibility. We can also have another type of phase transition where we are not stuck at randomly guessing. Instead, we are immediately doing better. But then the phase transitions is towards the exact recovery of the signal. And that's something that happens in, for instance, sparse linear regression in a second order manner. Or if we solve the sparse linear regression or some simple neural networks that I will be talking about tomorrow, then we have a first order phase transition. Or we have neither the random guessing or perfect recovery threshold, in which case the curve may be just smooth, no phase transitions, or wiggle in between nothing and perfect in the above way. And again, for each of those, we have examples in computational problems. And the number, remark on this connection with sum of squares and some line of work that establishes for a large class of algorithms the meaning of these phase transitions. That's something that relates to only these, where there is a phase transition between just randomly guessing and something better. So, okay, that's interesting. But there is whole zoology of types of phase transitions and phase diagrams, like we have in physics. And the number of problems where this type of methodology can be applied and these kind of graphs plotted, and in some limit, when the system is large, either proven or conjectured to be exact depending on the case, is long. Neural networks, linear regressions, inference on graphs, lowering estimations. This is just a list from my own works. I guess there will be 2 or 3 more slides like that if I actually wanted to include everything there is there or that I'm aware of. So many possible kind of variants of computational combinatorial problems where this type of analysis can be done and was done. In the last 10 minutes or so, let me ask the following question. You have this hard phase. It's both, okay, it's theoretically very intriguing, but can we get rid of it, at least sometimes? And this is a beautiful story, kind of going back into how the understanding of where the computational difficulty comes from may help us develop better algorithms. Because this is one of them. So now I need to change the problem, and from kind of playing card games with you on graphs, I go to something a bit more concrete and applied, which is compressed sensing. That's a beautiful idea coming from signal processing, where you realize that natural signals are compressible, as we know. Okay? And hence, since we can compress them, the idea is, cannot we measure them directly in a compressed way and then decompress them computationally? Why would this be interesting? Very concretely in, say, nuclear magnetic resonance imaging in hospitals, if we could actually keep the patient there for shorter time while getting the same reconstruction of whatever is the medical issue that we actually want to examine in them, that would be great. And this idea of compressed sensing, of measuring a signal with fewer measurements, taking advantage of the fact that in certain bases the signal is actually sparse. Many of the components are almost zero, and if we set them to zero, there is essentially no loss of performance, is very concretely speeding up the machines. So one of my former PhD students then works with Philips, so he tells me that with compressed sensing they get a concrete acceleration of about 2.5 on the machines, on the Philips machines that you may encounter in hospitals. There is an additional acceleration of 2 that I will mention tomorrow, for which they need to ship the hospitals new software and a GPU. And that's he told me concretely what they do. But I will mention that tomorrow, what was the new sparsity. But say 10 years ago, they get this acceleration of roughly 2.5 thanks to compressed sensing. So this is an important applied problem. Said mathematically, it's sparse linear regression. The matrix of, in regression, this would be the data, but looking at it as the inverse problem that is solved in signal processing, this is what is representing what is measured. This is representing which ray goes through which pixel if it was tomography, and which Fourier coefficient is taken in the MRI. So it's an inverse problem. I will kind of be setting it more properly mathematically tomorrow in a more general context. That has a phase diagram. We can analyze it in the same way, and as a function of how many measurements we saved, the alpha, and how sparse the signal was, we have again impossible phase, hard one, and easy with even a simpler method, which in this case would be just the lasso, just the L1 regularization. So we have a phase diagram like that. And we know here that as before, the nature of the transition between the easy and hard phase is this first order phase transition. And this is the phase diagram if this measurement matrix F is IID random, just random Gaussian matrix. Now the difference here is that it's us, engineers, designing the machine that measures. So it's us designing what the matrix F is. This is not the data that is given to us. This is the design of the machine. So if it was good for us, we can actually change the matrix F. And this is something that we can take advantage of and induce the nucleation in the behavior of the algorithm. So the nucleation that happens around an impurity, and that, just to make you understand, I still have 5 minutes, so I can do this little, I'm a physicist originally, so I have a demo. So now I will do, boss of the department, I should not miss. The guy who invited me, I should not miss. Okay, good, I have one for me. For the audience, I have a YouTube. There you go. So this is a little hand warmer. There is a liquid in it. There is a coin. So Michael, Philip, please pinch the coin and observe what happens if you pinch the coin. If I pinch the coin for the audience, this is what happens. This is working. Okay, now it's working. So there's a guy or girl, whatever. They go to pinch the coin, and it's liquid. You see it's moving. Now they pinch the coin. And now it's becoming white around the coin. What the white is actually the crystal, and he's like touching it, making you realize that this is solid. Right? It became solid. And now it's not liquid anymore, it's solid, everything. And what happened? It warmed, right? So there's the proof that the solid, physical proof, that the solid was the equilibrium here, right? It released energy. It had too much energy as liquid, it released energy, so now it's happier and it can warm our hands. So that's this physical concept of nucleation, and since in the compressed sensing we have the freedom of designing our matrix F, let me go back to my slides, we can actually do that. And all we need is we need the matrix F that somehow makes it low dimensional so that the volume eventually becomes bigger than the surface. And that's it. That's enough to make the nucleation. So we make it bend diagonal like that, with the first bend being higher, meaning that effectively in the first bend we have more measurements. So we are in the easy phase in the first bend. But then there's just the first bend, and we have many more. Those on average, dominate the kind of average number of measurements that we saved. But what starts in the first measurement then will nucleate, propagate in the same way the kind of crystal propagated through the liquid. And so that's an idea. And when we implement it as an algorithm, we just change the matrix, but still into something that in principle could be implemented, maybe not on an MRI machine, but on more kind of generic compressed sensing machine. And indeed, it shapes the hard phase. And this is what we suggested, and proof that this actually indeed destroys completely the hard phase came just a few months later. Kind of once the concept was there, in this case, the methodology was there. And this is just a demo in some sparse superposition codes example how the wave in the nucleation translates into the wave in your ability, in your error as a function of the index of the block. And this corresponds here to denoising some image over here. So the concept of nucleation can be borrowed to improve the sample complexity of this algorithm. We did not change the algorithm, we just changed the design of the matrix. But in cases where we have such a freedom, next to compressed sensing, the famous example are error correcting codes, where this spatial coupling can also be done. You kind of embed it into the design of your error correcting code. This is advantages. And with this, I will just end back with a bit more keywords for tomorrow and for Thursday. We will talk about null networks mostly tomorrow and gradient descents. And on Thursday, we will talk about optimizing in spin glass landscapes. And with this, I thank you for today.
Any questions?
So I have a question regarding metastability, and maybe I'm getting misled. So I was wondering, at some point you said that you entered this, there was a regime where the algorithm would get stuck, and then you call this a metastable state. But does it mean that if I wait long enough, the AMP iterations will actually get out of this, or do you need to nudge them to get out?
So the AMP, no, because the AMP goes to a fixed point and stays there. But if you are running the Monte Carlo Markov chain for exponentially long, it will get out. So not every algorithm, it depends on the nature of, but for the Monte Carlo Markov chain, absolutely so. But it would take, again, I mean, this is something about which there are no proofs, like that it actually needs exponential time, but that's the picture, that's the predictions here.
So, sorry if this is the wrong version, but so in the picture with the metastable logic, if you induce some crystal, they will crystallize the whole way through. So in your analogy for the three-colored version of this game, what if you knew in advance the color of some person? Does that propagate information?
Yeah, so that's a wrong intuition indeed, but people commonly kind of make the mistake, right? It's not enough to reveal something. That of course helps. The second order phase transition, it may destroy it, but the first order phase transition, it does not destroy it. It just shrinks it a little bit, but continuously so. For the nucleation, what is needed is not only to reveal something, but also to have this finite dimensional structure so that the surface actually loses over the volume so that this actually propagates. In the random graphs or high dimensional geometries in general, this will only propagate locally, right? If I reveal that you are red, okay, I know that the people with whom you're connected are not red. Okay, so locally there is some information, but not more than that. Whereas if, for a sufficiently big droplet, the surface was eventually smaller than the volume, this would actually propagate everywhere if the droplet is big enough. So this is missing there. It's not enough just to reveal a little bit and destroy it this way.
How cold is your very pure water for the picture? What's the temperature of your very pure water? And
I
how pure-
admit I don't know. I never managed to reproduce this experiment myself. I would guess something like -5 Celsius.
Not that cold. Yeah, not that cold. My wife has done it.
Okay.
Yeah,
And also not that pure.
I got this idea of a hand warmer in a glass conference in Japan where they handed this as conference goodies. And another conference goodie at the banquet of the conference, they served super good sake. So there, yeah, you can concretely do that. But I don't know what exact temperature. Not too cold because the colder it is, the more fragile the metastability is. Concretely.
A very practical question. How long does this stay warm?
Half an hour or something like that, it dissipates, right?
And then we can reuse it.
You can reuse it, right? You just need to boil it. And yes, I realized I did this demo a few weeks back in Cornell that, in Europe, in hotels, you have a kettle, so I can boil it. Because you cannot bring it liquid to the airplane. But in the US, I realized... in the US, I realized...
If you showed that, they would take you away.
I realized that it's always an adventure when I come back and need to boil it. So in Cornell, it ended up that some postdoc took it home and boiled it at their home. And anyway, there was one more question over there.
Like, you talk about these phases. I guess my question is like, can you say anything about like what happens at the boundary of these phases, or like how exactly phase transitions?
Yeah, so the boundary of these phases are given by existence of the fixed points in what I was showing this belief propagation equation, but tomorrow this will be a slightly simpler equation, just one variable equation. So you have some fixed point equation, and you just try to look for all the fixed points there are. And then what happens if I go back to one of my diagrams here, for instance? What this concretely is, this is the picture of all the fixed points that they are. So blue and green are the stable ones. Red are, no, that's not completely correct. Yeah, red are the unstable or subdominant ones. The unstable ones are the dashed ones. Remember my color code? And so you examine all the fixed points, and then at some values of the signal to noise ratio, the fixed points disappear because the stable one becomes the unstable one, kind of in bifurcation, right? Fixed points can change into one another, like in certain ways, but this one disappears. So the point at which this fixed point disappears, or turns into the unstable one that goes in the other direction, that's sharply defined. That's just defined as a property of the equation of, in some of the simple cases, just one variable fixed point equation. So that's what defines these boundaries, alpha d and alpha alg, disappearance or appearance of the fixed points. And then this boundary alpha it, that's where the free entropy of one of the fixed points crosses the other one. So when we have more of them, we compare the free entropies.
Yeah, I guess my question is more like, what if you set like the alpha to be exactly equal to the boundary value? Like, what happens to the system or the algorithm?
Okay, so that's right. Statistical physics of past century, say the second half of past century, studied these properties, right? The criticality close to the critical points. Like what happens is very interesting. When I teach statistical physics, I do demo to the students what actually happens around the 3 critical point in water. And you see kind of very interesting critical behavior, and then in which way the different quantities diverge around these critical points. That's what kind of statistical physics is. A lot of it is about. And these days in mathematics also this is very important topic. For instance, one of the last Fields medals for Hugo Dominique Chopin, he studies this kind of critical behavior in the Ising model. So in simpler models than what I'm talking about Hamiltonian-wise, but on lattices. Lattices are more complicated than random graphs. So there you need some like beautiful math to actually describe this critical behavior. So in physics that has been, say, established, a lot of it in the last century. From mathematical point of view, this is a whole domain studying precisely the neighborhood of these critical points. More in the second order phase transitions, like magnet is this. But then existence of the first order phase transitions in the Potts model, for instance, that's an interesting question. So there is a whole another subfield of mathematical physics that is related to that.
You showed how using these message passing algorithms, optimal methods for finding the minimum energy states of these spinning glass models. I was wondering, where do physical computers like coherent Ising machines fall on the spectrum of algorithms? Can they also be comparable?
So that depends in the sense that they don't enter the hard phase. That would be very surprising, right? Some people try to, David here in the audience was making comments that there are some papers that would want to say that with quantum computers or graph neural networks or fancy things, we actually enter those hard phases. Those are all flawed, as far as I know. I mean, that's not true. Now the question is, do they actually reach these optimal thresholds, or are they suboptimal? So that depends, right? For instance, what I was saying about the sampling, I will talk about it more tomorrow. That actually, to me and most of the physicists I know, it actually came as a surprise that Monte Carlo sampling cannot sample sharply correctly down to the algorithmic threshold. Okay, we kind of did not anticipate that. So, and that's because it's some physical procedure that kind of directly works in the configurational space, whereas to actually sample, you need to do something based on the marginals, and the diffusion models are doing that, etc. So it can be suboptimal. It depends on the physical mechanism. So to me, that's kind of a one way to put how this is also useful. It's a bit like in information theory. Now that you have the Shannon capacity, you can try to reach it. So which algorithms reach it and which do not. Right now we have these thresholds, we can try to reach them in a specific setting, but the kind of ideas behind which algorithms reach them can be more general or not. Okay, I mean that's more like wishful thinking, but sometimes it works. They are actually more general. So yeah, that depends. Either they reach the thresholds or they're suboptimal. Would depend on which specific setting we are talking about.
Okay, thank you. Yeah, maybe we keep the questions for after.
Come to ask your questions.
Okay,
I
thank
can
you,
stay here
Lenka.
further.